attention to is the voltage transfer characteristic, VTC, okay? This is the most basic one. Later, you will understand why inverter is so important, okay? When we do a more complicated logic, we use the same similar equation to derive everything. So there are a few important metrics I want you to know, right? One is the VM. VM, what does it mean? It means the input equal to output, right? I say VM equal to F of VM. This is function F, right? So basically this is VM and this is VM. And this 9 is 45 degrees. Just a definition. You need to memorize it, okay? And we also have output high, output low, right? This is output high, right? When the input is low. And this is output low, when the input is high. We have been talking about CMOS. We are used to CMOS. So nowadays, we actually always think that it has to be something like that. Hey, isn't that input low is 0, output high is VDD, right? This is the so-called CMOS, right? But this is not all the case. And in particular, in the old time, or even nowadays, we have some logic that does not guarantee the output low equal to 0 or output high equal to VDD. So by definition is output high is that you input output low. Output low is when you input output high. Is that okay? So for example, in this figure, the output low, where first find out output low is this one. So then I input output low, and then I find what is the output high. And with the output high, then I put output high as the input, and then I find out what is the output low, right? So in CMOS, maybe you can tell me, what is output high, working CMOS? I just mentioned about that, but just can you tell me what is, anyone, what is output high, VOH?
That will be the saturation, VDS saturation.
VDD.
VDD, yes. Saturation, you mean you saturate to the VDD, right? Maybe,
yes.
Maybe, okay, good. Sorry, maybe I should really draw the figure. Maybe this is some, please really stop me, right? You are helping the other if you have any question. This is VX. This is V out, VY. This is VDD. You know very well, right? So V output high is VDD, right? Then how about output low?
Ground.
Ground, 0. Thank you, right? But we have something called pseudo NMOS, right? We do use it sometimes. What is that? It just we use the resistor as the loading. Okay. Now, can you tell me what is output high?
VDD minus the drop at the register.
Almost, but think carefully. I'm asking output high. What will be the input when it is output high?
VDD.
VDD. Like when the input, yeah. So one is telling me the answer, right? Output high is the F of output low, means low input, right? So it means the NMOS is what? On or off when the input is low?
Off.
Off, yes. So if NMOS is off, what is the output?
VDD minus drop across the register.
Okay. You just tell me this is off. And do we still have drop?
There won't be any current, I think so.
Correct. There will be no current, right? So there will be no drop because I equal to 0. So this one will be charged up to VDD, right? So this is a trick, very tricky. Be careful about that. So output high is still VDD because there's no current going through it, right? This is the blue case, right? Is this clear? Any question? How about the green case? How about when output low? Output low means that the input is high, right? Input high. Good. Input high. What happened to NMOS when it's high? On or off?
NMOS should be on.
On. Thank you. Then what is the output now? That is what you just told me, right? Because now the circuit becomes this. It becomes a potential divider, right? This is NMOS because it's on, correct?
Mm-hmm.
So it's going to be what you said, VDD minus I times R. Is that okay?
Yes.
Okay.
Yes.
Of course, I don't know what is I. We need to solve it. We are going to solve this in this class, do a lot of this. Okay, so but the main point is just remind yourself for VTC, we have VM. Hopefully this is very straightforward, 45° 9, input equal to output. And then we have so-called output high, output low. That really depends what is the meaning of output low and output low also, because we're going to plug into the input. But unless it is CMOS, which is so nice, output high, output low equal to VDD and 0, other circuit can give you something not that nice. And that is going to affect the noise margin and also power consumption. Right? But we will discuss more later. Any questions? Okay, so we learned 3 important matrix. You're sure that this will appear in your midterm. And then another matrix is VIH and VIL. It is where you have the slope equal to -1.
Professor,
Yes.
I had one question with respect to the previous slide.
Mm-hmm.
So how do we determine the VM?
How do you determine the VM? So
Yes.
graphically, you just draw a 45° 9, then you will get VM. The crossover is VM equal to VM, right? Graphically. But
what about the voltage? Like, how do we relate with respect to the input and the output voltages?
The input is on x-axis, output is on y. So this one you draw a vertical line, then this is the VM that make you equal to. Are you trying to say this inverter? This is the meaning, input equal to output. That is VM.
Okay.
The voltage that make the output equal to itself is VM.
Okay. Yeah, okay. Got it.
But yeah, and then if you want to solve it analytically, you solve this equation, which we are going to do later. Okay, good question, right? Other questions? Okay, you ask anytime, right? So slope, what is this? What is the meaning of slope? Partial V out, partial V in. Looks fancy, but after all, you're just saying that this slope equal to -1. We have 2 points. One is VIL, one is VIH. Means V input high and V input low. So what's so special here? I don't say it yet, but why is special? Because you see that when you are outside between these 2 slopes, you have a very steep slope. You can just assume that this region is like a straight line, because an ideal inverter would be something like this, right? This is the ideal one. Very steep, very steep. So this is just approximation. We say that, okay, the point you give me -1 is just like this one. Right, the slope equal to -1. In this region, it's so steep, we call it undefined. Why? Because you move a little bit, your output can go from high to low, right? Just here, I have a little bit noise, it go to high to low. That's why VIH and VIL has some very special meaning. I'm going to show you exactly what it is. But from here, you see that I just move a little bit. I have this undefined region. It is actually defined, but it's just that it's very vague. If just from this graph, right? It is very steep. So that's why we call it undefined. Is that okay? So an extra quantity, right? You did not learn anything new except that these are the 2 points, give you slope equal to -1. I want you to memorize it, okay, for your interview also. But why they're important? That is here. You see that VOH is always larger than VIH, right? So the distance between VOH and VIH is called the noise margin height, which is equal to VOH minus VIH. And then we also have another noise margin called noise margin low, NML, which is equal to VIL minus VOL. But why this is important? Why I define this one, right? Why I want to define this noise margin? Think about an inverter train. Right? Ideally, if I put 5 volt here, let's say, let me use VDD. Let's say if this is VDD, I hope this output to be 0 and this to be VDD. Correct? Any question about this?
No problem.
Thank you. But unfortunately, I may capacitively couple to a noise.
Hey, Professor.
Yeah.
Can you point out the location of VOH and VOL on the y-axis?
Here. This is VOH. This is VOL.
And for the VOL, I see it's corresponding to the black spot on the right. And is there any reason you like is there any reason like you single out this the black spot?
Very good question. Yeah, because by the previous definition, when here VOL is when the input equal to VOH.
Okay, I got it.
Very good. Right, this is a very confusing part. Input, output. So you need to do it iteratively. Find a way. Just you need to, if you cannot solve equation, you just try different way. Okay, let's say this is VOH, then I get VOL. Then I get VL, I see if this is VOH. Okay, then I move to the right place. But otherwise, this is definition. Okay, VOH, that's why I single out this point, VOH. Very good. Same for here. This is VOL. Okay. Maybe confusing, right? We're talking about input. Why we have output? This is just the value. The value equal to VOL as the input. Okay.
Yeah, that's how I understand it. Like, I mean, you can like how to say, rotate the axis like by some 45 degrees, some degrees. You can make a x-axis become y, y-axis become x. Then that makes sense for the VOL and VOH.
You're right. Yes, rotate it, but do not rotate this graph yet. Only rotate axis. Okay. You rotate it outside of the plane. Okay.
Got it.
Good. Now.
Thank you, Professor.
Great. Very great question. Right. Now, what if we have noise? Well, the noise, if I make this one, if I increase VDD by very high value, the output is 0. No problem. I welcome this type of noise, except for reliability or some leakage latch up current issue, right? The one possibility is this will reduce my value by NMH, coupling noise. This is possible, right? You have a capacitor coupling to another wire. Another wire has a rapid transit, and this one has a RLC drop. Then the input become VDD minus NMH. What will be the output? Then let's look at this. VDD or So here maybe here I keep saying VDD because I assume it is the CMOS, right? Let me be more specific. Call it VOH, VOL, VOH, right? So you see, I was trying to input VOH. You give me VOL, which is good. But now you couple a noise, bring me down here. NMH. You make a noise, then my input essentially become VIH. What is my output? Well, because your noise is still smaller than the noise margin, then this one will still equal approximately equal to VOL. Right? This is still a, do you see what I mean? This still approximately equal to VOL, right? Because you give me VOH, okay, output is VOL. That is the green one. That is the ideal situation. Now, because of coupling noise, my input is actually VIH, right? VOH minus NMH. Yeah, the output increased a little bit, but still before this slope, output is still approximately VOL. Correct? And if your input is still, if this is about VOL, then after this stage, this output definitely is VOH. So this noise does not affect anything. But if your noise is larger than the noise margin, let's say instead of here, you come to here. And I just tell you, right? We can treat this as very steep because this is just all approximation, right? Then you may jump into this region and then your output will become VOH. And this one will become VOL. Your signal is completely distorted and game over. You have the wrong signal. Is this clear on what I'm trying to say?
Yes, Professor.
Thank you. Right, so there are different type of noise, right? Probably you know already. Let's quickly go over. You have the inductive.
Professor?
Yeah.
I had a question. So how do we relate the noise margin to that of the frequency?
To which frequency?
Input frequency.
Noise margin. There are many different type of noise margin. What we're talking about is the VTC noise margin. So here is not related to the frequency. It's only just related to the transfer curve, so which is just the difference between VOH and VIH.
Okay.
Yeah. But this just guarantees this steady state won't fail. But there are many other things can make your circuit fail.
Okay.
Yeah. Which has the frequency component. Now, but of course, the coupling strength is related to frequency. For example, you can have inductive coupling, capacitive coupling, right? You have two wires running over. You have a capacitance. You can couple the signal to there. So if your frequency is high, you will have more capacitive coupling. Okay? And also other noise coming from the ground and the power. This is something we need to redraw the picture in our brain. We always have to think about VDD is not next to you. I have a block A, a very big block in the chip, in the die, right? I have block B. Well, my VDD pin is here. Depends on how you route it. It can be like this. Okay, and then you connect this one to the, well, very bad drawing, sorry, ground, right? These are all resistor. So do not think that block A has the same reliability as block B. If it's steady state, even in steady state, you have the so-called IR drop. You don't really getting VDD to your transistor. You're getting VDD minus IR. And you don't really getting ground to your transistor. It's 0 plus IR. Okay? And then they have the noise coming from this source that can screw up your device, okay? After all, what is noise? Noise is something that you are not welcome. Yeah, that is not welcome, that you don't welcome, right? Which is the unexpected current and voltage. Okay, so noise is something you don't want or unexpected. If you expect it, even you don't want, it's not really a noise. You can do it before you take out your chip to reduce the effect. Okay. So there are several types of noise, internal noise and external noise. Fixed or some noise is proportional signals. Just now that student asked, right, how it's related to frequency, right? It also related to the swing also. Sometimes they are fixed, right? But let me just give you some example in the last 2 minutes of this class. How can we have noise? I actually kind of talk about the noise when we talk about the noise margin, right? For example, I have an inverter, still a CMOS, looks very good, right? I thought CMOS is very good device, no noise, but not really, right? You have a signal going in, for example, your signal is 1 volt. It has some wire resistor, right? This, hopefully, this is also 1 volt. But however, it is coupled to another wire, right? This is wire 2. This wire may suddenly change from 1 volt to 0 volt. Right? When this is 1 volt, let's say VDD is 1 volt, output is 0 volt, right? You suddenly go from 1 volt to 0 volt, you are going to pull down the potential maybe to 0.4 volt. And because you pull the 0.4 volt, maybe you turn off the device, this one will go to 1 volt. Right? It's not difficult to understand. For me, right, it was difficult to understand is that how come the 1 volt can be pulled to 0.4 volt, right? 1 to 0.4, this becomes 0 to 1 is okay with you. But how come this one can do that? That is because your wire has resistance. Yeah, in the source, I'm so strong, I put this at 1 volt. But here I have a large resistor. So if there's any coupling, you can temporarily put this to 0.4 volt because the other wire was doing the transition from 1 volt to 0 volt. And then you screw up the data. But this is just a transient, okay? Another is the so-called clock logic. In this clock logic, you have a clock here. And then you have another clock bar. And you store the data here. Now, the problem is this. For this type of logic, you can even destroy. It's just like similar to what we had before. You might go from 1 volt to 0 for this one, and this one go at 1 volt to 0.4 volt. Even it is restored, you actually discharge it. Sorry, this I need another case from 0 volt to 1 volt. So this was off, right? So this may be VDD. But you temporarily turn this on, it's going to discharge the circuit. And then you erase the logic, okay? We're going to discuss this in the future, right? But basically, when you scale it, it's getting worse, okay? I'm not going to spend more time on this. The noise is an issue, okay? Sorry, I'm slow, so I overtime already. Let's stop here. Any questions? I will stay for a few more minutes.